So I'm going to work through some of these logarithm problems just so you have some more things to look at. So I'm going to start with the harder ones, which are actually, it's not really the harder ones, these are the first ones. So problem 46 says h of x is equal to the natural log of 2x squared plus 1. And we're asked to find the derivative. So this is just a straight chain rule problem. So we're going to say h of u is the natural log of u, and u of x is equal to 2x squared plus 1. If I plug that back in here, I'll get to my original expression. So I take the derivative, and I get 1 over u, and I get u prime of x. Just a simple polynomial derivative. So we get u prime of x is equal to 4x. 2 times 2 is 4, and reduce the exponent by 1. So h prime of x is h prime of u times u prime of x. U prime of x is 1 over u. H prime of u is 1 over u. U prime of x is 4x. And we substitute in for u, which is up here, 2x squared plus 1 times 4x. So our final answer is 4x over 2x squared plus 1. We don't have any arbitrary constants because we're doing the derivative part. This is the slope of the line, this line here. And x could be any value, because if we let x be negative, it gets squared, and therefore it's always going to be positive. So the domain is good. All right, problem is 49. And we have y is equal to the natural log of x times the square root of x squared minus 1. So the first problem we did, 46, you really couldn't use any properties of logarithms. But in this case, we can. And let's call it f of x just to give it something else. Same thing, basically. So first property of logarithms we're going to use is that a product of two terms in terms of logarithms is the same as the terms by themselves added together. So we get the natural log of x, which is the first time. And because they're both in the numerator, we get them both added to each other. So that's the first thing. Now we can rewrite the second term as a fractional exponent. So this becomes the natural log of x squared minus 1 to the 1/2 power. So we haven't finished yet because we have an exponent, and we have the exponent over the entire argument. So we can bring that outside of the integral. So we get the first term stays the same, and then we get 1/2 times the natural log of x squared minus 1. So now that's where we want to be before we take the derivative. We use the properties of logarithms to expand the expression and get rid of any exponents we could. And so f prime of x is 1 over x, that's the derivative of the natural log, plus 1/2 times. So we get 1 over x squared minus 1. And then we have the chain rule, which says that we take the derivative of what's in the parentheses, which is 2x. So you can go back to the previous problem and see how the chain rule works. But that's always, you always take 1 over this quantity times the derivative of that quantity. So at this point, we can simplify things. This 2 cancels out with that 2. So we get x divided by x squared minus 1. And we probably would go one step further and find a common denominator, which is going to be the two denominators multiplied together, and then we cross multiply. So we get x squared minus 1, and then we get x times x plus x squared. So these can't, actually those add, don't they? Yeah, so we get 2x squared minus 1 over x times x squared minus 1. So I'll make sure everything looks okay. Break these apart, change that to fractional exponent, move that up front, take the derivatives, 1 over x, get the 1/2 from here, 1 over whatever's in the parentheses times the derivative of what's in the parentheses. These cancel out. Multiply the denominators together, cross multiply the numerator and the denominator, so we get x squared minus 1 plus x squared. These two combine, and so that looks pretty good to me. Okay, our next problem is 54. First I thought it was, how do we 54? No, it's 50. Okay, so we have y is equal to the natural log of the square root of x squared minus 4. Again, we look to see if there's any properties of logarithms that we could use, which you can if we rewrite this as a fractional exponent. And so we can bring the exponent out like that. And at that point we can take the derivative, so we get 1/2 times, okay, take 1 over the term in the logarithm times the derivative of the term, which is 2x, and these cancel out, and we get y prime is equal to x over x squared minus 4. So that's the answer. '54. So let's see what we have. We have h of t is equal to the natural log of t divided by t. And in class I mentioned to you that this is just using the quotient rule, because there is no properties of logarithms that can help here. If we had the integral of this, it would be a little different, but in this case it's just using the quotient rule. So let's redefine it as f of t, just to be in the same. Actually, it's good it's h of t, because then we can say the numerator is f of t is equal to the natural log of t, and g of t, which is the denominator, is t. So we can take the derivatives of each one of these separately. And so we get 1 over t for this derivative, and we get 1 for that. So we identify the numerator and the denominator, take the derivatives of each, and then we say h prime of t is equal to the quotient rule, which says you take g of t times f prime of t. So we take t times 1 over t minus this part, which is the natural log of t times 1, all divided by the denominator, which is t, and we square that. So the first part is 1, and the second part is the natural log of t, and we divide by t squared. So that's the answer. 1 minus the natural log of t over t squared. And that's about as far as you can go for that one. Just trying to think if there's anything that I need to tell you. I can't think of anything. Yeah, the only question is, which way does this thing go? Is it negative? Which one do I multiply? We always do the cross multiplication, and the way I think I'm remembering these days is you always do g of t, because that's the denominator. So we're going to do that without the derivative, and then the part that's subtracted, the second part, involves d prime of t. Well, let's see what we have next here. We have 57. So 57 is y is equal to the natural log of the square root of x plus 1 divided by x minus 1. So again, we're still doing using properties of logarithms. So this is going to be the natural log of this big thing to the 1/2 power. So because this exponent applies to the whole thing, we can bring out the exponent. And now we have a numerator and a denominator, so we can use the second property of the logarithms, which says that we can rewrite this as the natural log of x plus 1 minus the natural log of x minus 1. The reason it's minus because it's in the denominator, positive one's in the numerator. So now we've simplified it considerably. So all we have to do now is take the derivative. So y prime is going to be equal to 1/2 times the derivative of this, which is just 1 over x plus 1, times the derivative of this, which is just 1, so it's just 1 over x plus 1. And we subtract off the second derivative, which is just 1 over x minus 1. And so we could combine like terms. Let's see what happens. So what we'd have, again, we only have two terms, so you'd have x plus 1 times x minus 1 as our common denominator. These two multiply together. And then we'd have x minus 1 minus x plus 1. It's negative because I'm having this times negative 1 and this times positive 1. So I get 1/2. In the numerator, x minus x is 0. I get negative 1 plus a negative 1 gives me negative 2. So I get negative 2 in the numerator. In the denominator, I get x squared minus 1. If I multiply this out, you get x times x is x squared. You get plus x minus x, which is 0, and you get negative 1 times squared, which is negative 1. And you see I can cancel those out. This cancels out with that because one's in the numerator, one's in the denominator, becomes 1. So you get negative 1 over x squared minus 1. So that would be the simplest form of the derivative. But what we did is we used the properties of logarithms by rewriting this as a fractional exponent, taking that out, using the third property of logarithms, then using the second property of logarithms, which is the quotient. We took the natural log of that minus the natural log of that, then we took the derivatives, and then we combined them. Okay, what do we got next here? We got number 64. 64. And 64 is just a chain rule problem. If you remember, we talked about in class that the derivative of the absolute value of x is equal to just 1 over that. So even though we have an absolute value sign, it really doesn't change things that much. We still would say u is equal to, well, actually f of u. We'd say u of x is equal to the cosecant of x. F of u is equal to the natural log of the absolute value of x. So we take derivatives of those, and we get 1 over u. That should be 1 over absolute value u there, not absolute value of x. So we get 1 over u. If it had been natural log of just u, it would still be 1 over u, so it doesn't change. U prime of x. The derivative of the cosecant is, I think it's negative cosecant, cotangent or something like that. But if you forget what those are, you can go back to the second chapter. If I can find the formulas. There it is. So 250 you kind of remember, but we also have page 136, which is a summary of differential differentiation. So if you look at d dx of the cosecant of x, you get negative cosecant of x, cotangent of x. That's cotangent, not tangent. Okay, so we have cotangent of x. So f prime of x is f prime of u times u prime of x. F prime of u is 1 over u. U prime of x is negative the cosecant of x, cotangent of x. Then we finally substitute in, so we get, so what do we get here? We get negative the cosecant of x. I always have a hardest time with that. What is cosecant of x, cotangent of x divided by u, which is the cosecant of x. You can see we have a cosecant in both the numerator and the denominator, so you get this is equal to negative the cotangent of x. Just like we've looked at before, you know, if this is the derivative, then the integral is the opposite. So if you integrated the cotangent of x, you would end up getting negative the natural log of the absolute value of the cosecant of x. So we could do that. We're going to prove that in the next section, but we already shown it here by taking the derivative, and then we could go back in the other direction. Okay, we're in 68. Still on page 136 from the last problem. So bear with me here as I go back to section 5.1. So 68 is kind of a combination here. Y is equal to the natural log of the square root of 2 plus the cosine squared of x. So what can we simplify this by using the properties of logarithms? Well, yes, we can once we write this as a fractional exponent. So we can bring that outside because this is applied to the whole thing. So we get y is equal to 1/2 the natural log of 2 plus the cosine squared of x. Now the temptation would be to just do these separately somehow or another, but anytime you have something that's two terms that are added together in here, that's as far as you can go. So this is where we are. We at least got rid of the square root thing. So we're going to choose, let's say, f of u is 1/2 natural log of u, and u of x is the term in the parentheses, cosine squared of x. So we take the derivative of each one, and you would be tempted to say this is just 2 times cosine of x, but remember that doesn't work that easily, unfortunately. Okay, f prime of u would just be 1/2 times the derivative of that, which is 1 over u. U prime of x. Okay, we have to, let's rewrite this. U of x is equal to 2 plus cosine of x quantity squared. So we always want to rewrite it as that. This is just for compactness. But if we see something like, we want to rewrite it as that. So when we take the derivative of u, this goes to 0. And here we have to bring the 2 down. Then we have the cosine of x to the first power by decreasing the exponent by 1. But you have to use a chain rule, so you take the derivative of the cosine, which is negative the sine of x. So that's the part people would mess up. So you got to be careful. Recognize this as a chain rule, and this is really 2 parts of the chain rule. I did this one so I didn't have to add another term, but you take 2 down, reduce the exponent by 1, keep that the argument of the exponent the same, exponential part. This is the base basically, and then take the derivative of the inside. So let's just rewrite this and before we start substituting back in. So here we have 1 over 2u, and u prime of x is going to be equal to negative 2 the sine of x cosine of x. So I just move that in front. Sine usually comes before cosine if there's any choice. So let's go to the next page. So now we'll substitute it in. So f prime of x is equal to f prime of u, which is 1 over 2u times -2 sine of x cosine of x. Then we make the u substitution. So we get 1 over 2 times u, which is, what is u? 2 plus cosine squared of x. So that's u times -2 sine of x cosine of x. There's really not a whole lot we can do here. So we just, we would cancel the 2's out and we move the negative sign in front. So we have negative sine of x cosine of x divided by 2 plus cosine squared of x. And that would be our final answer. Okay, so 71 is a little different. This is finding the equation of the tangent line, which we haven't done for a while. But if you remember, what we do is we calculate the derivative, plug in the number x to get the derivative, the value of the derivative. That's the slope of the tangent line. Then we use the point slope form of the linear equation to get the final result. So the only difference is that we have our function involves a logarithm, whereas before it hasn't. We just have something new to mess with. So you can see if I stick 1 in here, if I did f of 1, I'd get 3 times 1 squared minus the natural log of 1. Natural log of 1 is 0, so you get just 3. 3 times 1 minus 0. That's where the 3 comes from. Okay, now we're going to take the derivative. And because this is separated, we're not going to use any properties of logarithms because we just have this derivative of this minus derivative of that. So you get 6x from here. 2 times 3 is 6. Do 6 1 by 1. And you get the derivative of the natural log, which is 1 over x. So that's our expression for the derivative. Then we find f prime of 1. So we get 6 times 1 minus 1 over 1, which is 6 minus 1, which is 5. So we find the slope of the line, of this line, at x equals 1 is equal to 5. So with that slope, we can say that's m is equal to 5. And remember, the point slope says y minus y1 is equal to m times x minus x1. So in our case, y1 is just this number, 3. Our slope is 5. X is the variable. X1 is 1. So that's, we just plug them in, and then we multiply out the right-hand side. So we distribute the 5 to each term. And then we add 3 to both sides, so we can solve for y and get the equation in the slope-intercept form. So that's your final answer. Y is equal to 5x minus 2. So let's just prove that we did it correctly. So I'm going to write that answer down. We're going to go to the graphing program. So the original function is 3x squared minus natural log of x. The equation for the tangent line at x equals 1 is 5x minus 2. So let's see if I did it right or not. So the function, the original function is 3x squared minus the natural log of x. And the second straight line is y is equal to 5x minus 2. Must be doing something wrong here. I wondered about that. I think I got to put parentheses around the natural log. Okay, graph. So there you go. So if we went back to here, this is my straight line. This is my function. At x equals 1, the slope is 5. And if I zoom in on that like that, you can see that this line, the blue line, is tangent to the red line. So everything's as it should be. So our final group here is using logarithmic differentiation. So we're going to start with 93, which says y is equal to x times the square root of x squared minus 1. And we could solve this. We could use the product rule, where this is one part, this is the second part. The second part, we have to use the chain rule to evaluate that. So it's probably easy, just as easy to do it either way, but we're gonna demonstrate it here. So what we do is, when you use logarithmic differentiation, you take the log, the natural log of both sides, like that. So I'll just put ln. So then you use implicit differentiation. On the left-hand side. So you always end up with the same thing, natural log of y. So when you take it, you get 1 over y, which is the derivative of that, and then you multiply it by y prime to do the implicit part. And actually, we don't want to use that yet. We're going to use it here in a second. First thing we're going to do is use the properties of logarithms now to break this apart. So we get the natural log of y is equal to the natural log of x plus the natural log of x squared minus 1 to the half power. So I've done two things here. I changed that to the half power, and then I broke it apart. And then the final thing is I can take that 1/2 out as an exponent and just give you that. So that's what the whole purpose of taking the natural log of both sides is, to get that simpler. So now we take the derivative of the natural log of y. We get 1 over y times y prime. The derivative of the natural log of x is just 1 over x. Then we get 1/2 times, okay, the derivative of the natural log of that quantity is 1 over that quantity times the derivative of that quantity, which is 2x. So we get 1 over y times y prime is equal to 1 over x plus, well, the 2's cancel out, so we get x over x squared minus 1. Now, so now what do we do? Well, let's combine these with a common denominator. Again, because there are two terms, the common denominator is going to be just the product of the two. And then we do the cross multiplication. So we have x squared minus 1 times 1 plus x times x, which is x squared. And so we end up with 2x squared minus 1 over x times x squared minus 1. Okay, now multiply both sides by y, so we get y prime is equal to y times 2x squared minus 1 over x times x squared minus 1. But we go back to the original equation to look for y, so what we get is that the derivative in terms of x, completely in terms of x, is going to be y, which is x times the square root of x squared minus 1 times this quantity in the brackets so we get that. And we do a little simplification because we have x here, we have x there. We have this to the half power divided by this to the first power. So the final answer is going to be 2x squared minus 1 divided by x squared minus 1 to the 1/2 power, or we can rewrite it as x squared, 2x squared minus 1 over the square root of x squared minus 1. And I'm just going to check the answer here because I need to make sure I didn't mess up or anything. Okay, check the answer, and I did okay, so that's good. Okay, so next one, 95. So we have y is equal to x squared times the square root of 3x minus 2 divided by x minus 1 quantity squared. So now we're getting to the realm of where this really helps out a lot. The first problem we did, 93, yeah, you could do it easily either way. Well, I'm not sure easily, but it would probably be equally easy or equally hard, depending upon your perspective. So, because this involves products and square roots and squares and stuff, it's ripe for using the logarithmic differentiation. So we take the natural log of both sides. Okay, so before we take the derivative, we're going to separate all this stuff out. So we get the natural log of x squared plus the natural log of the square root of 3x minus 2 minus the natural log of x minus 1 squared. So these two terms are in the numerator. This one's in the denominator, so we subtract it. And then each one of these we can pull out the exponent. So we're going to have the natural log of y is equal to 2 times the natural log of x plus 1/2 times the natural log of 3x minus 2 minus 2 times the natural log of x minus 1 squared. Oh, take the square off there. We pull that out. So that's all we can do. Everything just got stuff added together in here, so that's as far as we can go. So we're going to take the derivative of both sides, and because these are all added together, we just do them separately. So the left-hand side just becomes 1 over y times y prime. The left-hand side becomes 2 times 1 over x for the first derivative plus 1/2 times, okay, in the denominator we have 3x minus 2. In the numerator we have the derivative of this, which actually is 3. Not 3x, but 3. And then we have minus. The derivative of x minus 1 is 1, so all we have here is 2 from this constant and over x minus 1. So we did all that. Then you could solve for y prime. It's going to be equal to y times all this stuff, 2 over x, plus 3 over 2 times 3x minus 2 minus 2 over x minus 1. And then you can plug y back in. So you get y prime is equal to x squared times the square root of 3x minus 2 divided by x minus 1 squared, which is y, times this whole big shoot match here, 2 over x plus 3 over 2 times 3x minus 2 minus 2 over x minus 1. Now the question is, do we want to try to simplify this by finding a common denominator between all three of them and combining 3 terms and going from there? And the question is, well, the book does it. I'm not sure whether it's really worth it or not, but you know, this would be sufficient. But let's go ahead and do it just to see what happens. Because what's going to happen is there are going to be some terms here we can cancel out. But just to give you an idea of how do we handle this, well, it's kind of like the same way, except you multiply this by that, and you multiply this by that and that, and you multiply this by that and that to get the numerator. So let's see what happens. So we have our y term here out in the front. Excuse me. Okay, so that's the inside term. Then we'd have 2 over x times. Okay, so we're going to multiply by this and that. So you have 2 times 3x minus 2 times x minus 1. That's the first term. So we're dividing all this stuff by the same exponent, the same denominator, which is x times 2 times 3x minus 2 times x minus 1. Okay, so this is, I'm going to have more of the numerator at the top here. So we have 3 times x, 3 times x, 3 times, and times x minus 1. And the final term is going to be 2 times these two multiplied together. So we get x times 2 times 3x minus 2. So that's this negative 2 times that times that times that. And again, it's all divided by x times 2 times 3x minus 2 times x minus 1. Well, one thing you can see is that I could factor out x minus 1 and multiply it by that, so I get x minus 1 cubed. So let's see what we can do here. We're going to take this denominator and we're going to cancel out with stuff here. So this x cancels out with one of those x's, so we just end up with 1x. We get this divided by that, so we actually get in the denominator the square root of 3x minus 2. And then this term is going to be x minus 1 cubed, because we have squared and then we have multiplied by that, and we got a 2 somewhere here, 2. Okay, and that's all multiplied by all this stuff here, which actually I don't want that. I'm just gonna, okay, that's out of there. So if we multiply all this stuff out, we can combine like terms, and then we could all multiply by x. So let's just do it if you're really interested in how this thing works out. So I'm going to see if I can keep all this straight. I'm going to add another page so we can do this part out and see if we get it all right in the long run. So we're going to have 4 times this thing, which is going to be 3x squared minus 2x minus 3x plus 2. So that's the first numerator. And let's just put it in a column format here. Then we have this, which is going to be 3x squared minus 3x. And then we're going to subtract this last thing, which is going to be, let's see, 4. 2 times 2 is 4. And you get 3x squared. 3x squared minus 2x. So what if we got is 3x times x, 3x squared. Negative 2 times x is negative 2. Okay, so let's see what we got here. So so I'm just going to do this. You get 12x squared minus 8x. Well, we can combine these two into 5x. So this is going to be negative 2 minus 3 is negative 5. So we get negative 20x. 4 times 2 is 8. Okay, so this first one becomes that. Let's just line these up. So you get plus 3x squared minus 3x. And here we get negative 12x squared plus 4 times 2 is 8 plus 8x plus 0. So then we do all these together. These cancel out. So we end up with 3x squared. Negative 23 plus 8 is negative 15 plus 8. Okay, and then we multiply it by x. Well, let me just put this in here. So we get 3x squared minus 15x plus 8. So the final answer is 3x cubed minus 15x squared plus 8x divided by 2 times the square root of 3x minus 2 times x minus 1 quantity cubed. Okay, now I'm going to look at the answer book. 3x cubed minus 15x squared plus 8x over 2x minus 1 cubed. So that's it. So that's your final answer. So let's kind of repeat what we did here. Took the original expression, took the natural log of both sides, used the properties of logarithms, first property and the second property to break this up, and we brought the exponents out where we could. We took the derivative of both sides, which involves taking implicit differentiation of this, and then we have the 3 terms. So we got 2 times 1 over x plus 1/2 times 1 over 3x minus 2. And then you also multiply it by 3 because the derivative of that was 3. Negative 2 times the natural 1 over x minus 1. Okay, so then what we did is we multiplied both sides by y to solve for y prime. We plugged in y back into the original equation. Then what we did was we found a common denominator, which is this times that times that. Times that times that. And so to get this numerator, we took this times that times that. To get this numerator, we took this times that times that. And to find this one, we took that times that times that. So that was all this stuff. And then we multiplied all the stuff out, combined all the terms, canceled stuff out, blah, blah, blah. When we had this denominator here, we could usually cancel stuff out here with y. That always happens. Anyway, we got to the end, and we got the right answer, amazingly. Okay, and our last problem, 98. So again, this is implicit differentiation, or actually not implicit, but logarithmic differentiation. So we have this quotient involving 4 terms, which we don't have a rule for. So what we do is we take the natural log of both sides. And taking the derivative is actually the easy part of this thing. It's combining it back into something if you want to rewrite it. So we can use the properties of logarithms. So we have the natural log of x plus 1 times the natural log of x plus 2 divided by, or minus, I did that wrong, plus the natural log of x plus 2 minus the natural log of x minus 1 minus the natural log of x minus 2. So these are the numerator, these are the denominator. Those are added, these are subtracted. Okay, so now we can take the derivative. So you take the derivative and you get 1 over y times y prime. And the derivative of the left-hand side becomes 1 over x plus 1 plus 1 over x plus 2 minus 1 over x minus 1 minus 1 over x minus 2. So that was pretty easy. And to solve for y prime, we multiply both sides by y, so I'm just going to go ahead and plug y back in. So this is y. So that's y, and then we multiply that by y, the left-hand side, which is 1 over x minus 1 plus 1 over x minus 2 minus 1 over x minus 1 minus 1 over x minus 2. And so it's all in terms of x. So the hard part here is putting this all together. And I think I got a sign wrong here. What did this should be x plus 1. This should be x plus 2. So I'm just looking in the book, see what they do. They do a little sneaky thing here. They actually group these two together and group those two together. So if you do that, you'll have this big term in the front again. And then if you have this minus that, so let me just show you what they do. If you take 1 over x plus 1 minus 1 over x minus 1, again, you can use the cross product idea. So, because you have two terms, so you get x minus 1 divided by these two multiplied together, x plus 1 times x minus 1, and then so you get this times that minus that times that, and so this goes to 0. X minus x is 0. Negative 1 minus 1 is negative 2, so this becomes negative 2 over x plus 1, x minus 1. And likewise, the other group, which is 1 over x, what was it, x plus 1, x plus 2 minus 1 over x minus 2. Again, you can have this common denominator. And actually, there's one more step here, which I left out. If you multiply this thing out, the denominator just becomes x squared minus 1, because the inner and outer cancel out. And the same thing's going to happen here. So what you'll end up with is x squared minus 4 here, and we'll get x minus 2 minus, so we get minus 4, because the x's cancel out, and the negative 2, and you get a negative 2 minus a 2, so you get negative 4. Okay, so that's that part, and then you can combine these two terms into something. So we can then take, if we take negative 2 over x squared minus 1 minus 4 over x squared minus 4, and then you have two terms again, so you can just cross multiply. So we'll get negative 2 times x squared minus 4 times x squared minus 1, all divided by x squared minus 1 squared x minus 4, don't have to do that. You just get x squared minus 1 and x squared minus 4. So multiply that out, we'll get negative 2x squared plus 8 minus 4x squared plus 4, all divided by x squared minus 1 times x squared minus 4. And so you get negative 6x squared plus 12, all divided by this stuff. Okay. And you can actually expand this out again, so it's kind of like you contract it, but you expand it. So this is plus 12, and this becomes x minus 1, x plus 1, x minus 2, x plus 2. So all we're doing is this part right in here. So now when you take this and you multiply it by this, so let's just do that. So you get x plus 1, x plus 2 divided by x minus 1 times x minus 2 times negative 6x squared plus 12, all divided by x minus 1, x plus 1, x minus 2, x plus 2. So now I'm just going to add a page in here. And you can see the x plus 1's cancel out, the x plus 2's cancel out, and then you get x minus 1 quantity squared in the denominator. So we get x minus 1 quantity squared times x minus 2 quantity squared, all divided by negative 6x squared plus 12. And if you factor out a negative 6 or negative sign and then a 6, you'll get x squared plus 2, or x squared minus 2, x squared minus 2 divided by x minus 1 squared, x minus 2 squared. And that turns out to be your final simplified answer. So that's pretty intense as far as all the stuff you have to keep straight. So, if we got to this point, we just quit and said that's far enough. You can still plug numbers into here, get an answer. So, the rest of this is nice, but it's not entirely necessary. Anyway, if you got to this part, that'd be fine. This rest of the part, just for your information.